Okay, here we are. Question number 44. There's a little bit involved to this, but we'll make our way through it. So, start off by reading the question. You are coaching a little league baseball team. One of your players is having a hard time hitting the ball. He does a good job of choosing which pitches to swing at, but he keeps missing because his bat doesn't get around fast enough. That's kind of a key to come back to. What would you suggest he do? Give one suggestion, explain the reason. So whenever, yeah, again, if you get an open-ended question and you see something like explain the reason, usually that means using one of your equations to try to explain, but you can still do it in words. You'll see. And chances are if I ask you to give a suggestion and explain, it's probably going to be more like 2 marks. Yeah. Okay. Anyway, so yeah. So essentially, one of the first steps we can do here to help understand a bit better is draw a bit of a schematic of the system that we're looking at, right? So always thinking about our system. So we're going to have our batter here. We're going to look top straight down at this batter. You know, one of the things we're seeing is a round. So there's probably angular motion. And if we think about it, what we know about a baseball swing, there's rotation, right? So we can think first about our batter here, and heck, we'll draw the plate in. Okay, and again, based off of this information, we know that they're swinging, they're having some sort of rotation. There's arms. We also know in baseball there's a bat. So there we go, and let's get some force or something. Know that there's some sort of a rotation. If we were to make an axis down the center of the body, down the midline, there's some sort of rotation happening in some kind of a direction that way. Okay, great. So we're looking at this. We kind of have our schematic. And already we can start thinking of different ideas or different concepts that we've covered in class. You know, you can be thinking, oh, okay, well, maybe there's something to do with torque, or maybe something to do with like angular momentum, or if you're even thinking back, you know, way back, something to do with like angular acceleration or angular velocity. But if you think velocity and you think, okay, doesn't get around fast enough, well, we have some things that come up with force, acceleration, speed, etc., and length of radial arms, right? So if we're just purely thinking about how fast can some sort of a mass move or something like that, a common thread that will increase angular acceleration or is involved in angular acceleration and angular momentum is our moment of inertia. So let's take a look here. So capital I, that equals our mass times our radial arm or moment arm squared. The reason I picked that, again, if you're looking through your equations on your sheet and you kind of look at torque, you know, that's moment of inertia multiplied by the angular acceleration. Similar if you go to angular momentum, you know, you could find another moment of inertia times angular velocity. And the common denominator here that we're seeing is this moment of inertia. Okay, that's both involved in momentum, which you know can help produce, is related to angular velocity, or you know, if you're looking at torque, that's angular acceleration, right? So let's go back to our little schematic here. I'm gonna try something. Let's see if I can blow this up bigger. Okay, there we go. Great. Okay, so in this scenario, one of the things we're trying to do is change something. So give a suggestion to help get a bat around fast enough. Well, you know, if we want, let's say, our angular velocity or similarly related our angular acceleration to increase. Actually, you know what? I don't like that. I'm going to have to scooch that out. Okay, let's use green. Okay, yeah, green for increase, or go more or faster. Holding all other variables the same, excuse me, in that equation, we're going to want inertia to come down. Okay. Because if we've maximized the amount of torque or angular momentum that can be produced by a body, we want to play with one of the other variables. So we're looking here, going back to our little schematic, and if we're going to try to change something with an I to make it less, we're looking at our variables, and we can't really make our mass lower. Okay. So what we're going to do is we're going to try to change the radial arm, or the moment arm. Okay, so if we look here from the center axis, right, any angular movement is around an axis. So here's our angular, and if we go all the way along, say the arms are fixed in line with the bat, and we're going to say, just for keeping things simple, that when we get across the plate, typically we'll want the ball to hit the very, very end of the bat. We can say between the axis point and the very end of the bat could be our R. We can say that. Why not? Okay. So we can actually write this out, where if we want to, just kind of add a couple of variables together. So we could say the length or extension of the arms, or the R value of the arms at full stretch, plus the length of the bat at full length. So again, at the very tip of the bat to the very end, is where that ball is going to hit, and we're going to hold right at as close to the end as possible. We're going to have our R for scenario 1. Okay, and again, we're trying to change our. So what can we tell the player to do? Well, there's two things. We could suggest that they shorten. Sorry. We could suggest that what they do is they shorten their arm length by bending their elbows. So what we'd be changing in that is the length of their arms. But what we can actually do is, without changing the biomechanics of the way the player swings, what we can do is we can decrease R by asking them to choke up on the bat. So essentially what we'd end up doing in this scenario is, and I'll do it a bit exaggerated, you don't actually do this in baseball, but let's say they move, halfway up the bat. Okay. So now what's happened is we've halved the length of the bat. Okay. So we could say in our second scenario, R2, the R, or the length of the arms at full, plus the R will essentially be half. So R of bat choked, as in you choke up on the bat, so half of that length, that's going to be a lot less. So in this scenario, the total R in scenario 1 over here is a lot greater because the bat's at full length, whereas here it's like half bat. Okay, so if we look at this scenario and kind of carry that forward a bit into a bit of a comparative moment of inertia calculation, just to see what that looks like. The mass is going to stay the same in both scenarios. That's why we can purely look at the R's. But let's just say, for instance, the mass R squared, we'll call this 1 equals, and then mass 2 of R2 squared equals something. We're going to just pick a number for R to be in our first scenario here, we could say 10. It's 10R, 10 meters, whatever, So we got 10 meters, and so when you do the math, and we'll just say one mass, this calculates to be 100 roughly. But when you go, half of 10R, so we halved the length of this scenario, which ends up being 5, right? And you square 5, what you actually get is 25. So we can see by shortening the length of the bat here, what we've done is significantly, by 3/4, decreased the amount of moment of inertia in scenario 2, okay? So why is that important? What does that matter? Well, if we go back up here and we look at our equations with our variables, if we have a fixed torque or angular momentum that the body can produce, well, by decreasing the inertia, moment of inertia, by shortening the bat, we increase angular acceleration, and most importantly for this particular question, we increase angular velocity. Okay, and that's the goal, trying to get the bat to come around quick enough. So timing, biomechanics, all of that was there and fine, but really, yeah, we're looking here at how to increase angular velocity. A similar idea is, or angular momentum, right? And that will increase angular velocity. Sorry, no, I said that backwards. Go with the first thing I said. The angular velocity is what we want to increase. Okay. Yeah, so if you're to summarize this and pull it all together as far as how you might answer this on an actual exam, this was the full explanation. You wouldn't necessarily need to do that. You could pretty much say, your player can choke up on bat, and then you could say something like, well, L, angular momentum, I, angular velocity, and say if you want to decrease I, you want to increase W, and in order to, I've run out of space, sorry, I'll just verbalize it. So you say the player chokes up on the bat, so in point form, choke bat. 2, you can say you want to, given the same angular momentum, you want to decrease I, decrease angular momentum to increase angular velocity. Therefore, if you, the explanation for why you would choke up on the bat would be you're trying to decrease R ultimately to help all that pan out. Okay. And that was 44.